In this topic, we'll follow a cryptographic key's entire life inside a Luna HSM. You'll see how keys are generated, imported, protected, rotated, backed up, and finally retired, and how each of those decisions directly affects your application's security and reliability. So far, you've built 3 key layers of understanding. First, you learned how the Luna HSM is structured: modules, partitions, roles, and isolation. Then you made it reachable and trusted with client setup, network trust, and authenticated partition access. Next, you explored how key types and attributes drive application behavior. Now we shift from concepts to operations: how keys are generated, imported, backed up, rotated, and ultimately retired. That lifecycle view sets you up for PKCS number 11 integration in the next module. On a Luna HSM, a key is a long-lived object with behavior, not just a block of bits. You generate or import it, activate it, and your applications bind to its label or ID. Attributes decide whether it can encrypt, sign, or wrap other keys. Over time, you rotate versions, keep older ones for decryption and verification, and clone or back them up for high availability. Eventually, you retire and destroy keys, so policies stay clean and old secrets don't linger. Generating keys in software and importing them into the HSM introduces several risks. Keys can appear in plaintext in memory, logs, or temporary files, and different teams may each keep partial audit trails. Policy enforcement also depends on how carefully each system is configured. Generating keys directly inside the Luna HSM reverses these risks. Randomness and storage are hardware protected, keys never leave as plaintext, audit logs are centralized, and both policy and operations become simpler and more predictable. On the command line, key generation follows a consistent pattern. You start by authenticating with the correct role, so any keys you create are bound to the intended partition. Then you run a generate command, choosing the algorithm, key size or curve, and the required usages. Right away, you assign attributes like sensitivity, extractability, and a clear descriptive label. Next, you list objects to confirm everything matches requirements. And finally, you record the key metadata in your change and audit records. From the application's perspective, it's really just sending a recipe, not the key material itself. Your code logs in, builds an attribute template, then calls the HSM to generate either a symmetric key or an asymmetric key pair. Those attributes define what the key can do, where it lives, and whether it's ever extractable. The HSM returns only a handle, while it securely stores, protects, and enforces policy over that key for its entire lifecycle. Applications never handle raw key material. They work with labels, IDs, and attributes. Treat those as part of your API contract. A good label describes function, environment, algorithm, and sometimes version. A vague label like test key or prod1 almost guarantees confusion during failover or recovery. Pair strong labels with stable identifiers and precise attributes, so signing keys only sign, decryption keys only decrypt, and every environment can reliably find the exact key it needs. Choosing a key type starts with the job it needs to do. AACE is your workhorse for bulk data encryption and key wrapping. RSA and elliptic curve keys are ideal for signatures, TLS, and broader PKI workflows, with ECC usually giving better performance at smaller sizes. HMAC keys are designed for message authentication and API integrity. Before you commit, confirm that the algorithm, key size, and curves are actually permitted by your partition policy and your compliance standards. Import is what you rely on when you can't generate keys directly in the new HSM, for example, during a payment system migration. The goal is to move existing signing keys without ever exposing raw key bytes. That means using wrapping keys, secure backup files, or dedicated migration mechanisms, and obeying import policies. Any moment when plaintext keys appear should be rare, fully scripted, heavily monitored, and surrounded by compensating controls like dual control and time limits. Key wrapping simply means encrypting one key with another trusted key, so it can safely leave its home. The wrapping key or key encryption key turns your key into a ciphertext blob that can travel or be stored outside the HSM. When it arrives, the HSM unwraps it and recreates a managed key object. The critical controls are the attributes: whether a key can wrap, unwrap, or be extracted, and who is authorized to perform those actions. Think of import as a pipeline where plaintext is radioactive. Before anything moves, wrap keys at the source and decide exactly which wrapping keys are allowed to participate. During import, unwrap only inside a tightly controlled boundary and design the process so nobody can casually see or export plaintext. After import, verify attributes, IDs, and permissions, then record who approved what, when, and from where. If the process isn't auditable, treat it as not secure. Key rotation is more than just generate a new key. It's about managing overlapping states so your application keeps working. You introduce a new key version and start encrypting new data with it, but keep the old key available for decryption and signature verification. Versioned key IDs tell the application which key to use for each object, token, or record. Only after all data and signatures have migrated can the older keys be fully retired or destroyed. In a Luna environment, backup is about preserving encrypted key material, not dumping raw keys. The security domain acts like a cryptographic fence. Only partitions in the same domain can decrypt and restore those backups. That's why a random partition, even on the same hardware, can't import your keys. You should regularly test backup and restore, and verify that labels, IDs, and attributes survive the round trip before you rely on it in production. In production, you rarely depend on a single HSM. Cloning lets the same key material live on multiple partitions, so any node in the application cluster can continue encrypting, decrypting, or signing during failover or load balancing. The key constraint is the security domain. If domains don't match, cloning and restore will fail. Also, never assume keys are everywhere. Explicitly design and test provisioning, synchronization, and failover paths for sessions, object lookup, latency, and recovery. You've now seen how key lifecycle decisions directly shape reliability and security. Prefer generating keys on the HSM. Import or wrap only when there's a strong, auditable reason. Design rotation, backup, and cloning strategies before you go to production. In the next module, we'll turn these practices into code with PKCS number 11 and Luna integration patterns.